course, I know for a lot of people there's been power outages and internet outages. I haven't had internet since Wednesday night. If I want to check my email from home, I have to walk up an icy hill because I don't get any cell signal at my house. But if I walk to the top of the hill up on the ridgeline, I get maybe medium strength LTE. And so I did that a couple times. Let's get into some announcements here. Homework 4 is due on Wednesday, February 17th. So that's the nodal method. And you've already been working on that for quite some time, even before the current storms hit. And so where I kind of landed on this mentally, rather than pushing back the deadline for everyone, I'd like to keep the deadline as Wednesday, February 17th. And if for some reason you're not able to meet that deadline, will you please email me with just a brief description of the circumstances, and then we can work out a time extension. But you know, I kind of feel like time extensions are as harmful as they are helpful, because what it essentially does is it delays when you finish something and move on to the next thing. And so you're just delaying rather than you're delaying and getting less time to work on the assignment after it. So but if you do need it, please contact me. Now, homework 5 is going to be due on Wednesday the 24th, and I put that online so that you can start working on the Hardy-Cross method. Now, we're going to be talking about the Hardy-Cross method again today. It was first introduced in Friday's class. If you haven't already watched that lecture recording, please, I would invite you to do that, because it may help you to understand the fundamentals of this technique even a little bit more than today's more complicated method is going to be. So the Hardy-Cross stuff we're going to finish today, and then later this week we're going to start talking about topics like water hammer and surge tanks. And so those are the 3 topics that are on homework 5. Any questions related to these announcements before we get into this more complicated method for the Hardy-Cross method? More complicated example, that is. Okay, so this is the method, and the example that was illustrated in the lecture recording on Friday kind of talked you through the approach of the procedure. And what we're trying to do in the Hardy-Cross method, remember, is we're trying to figure out how much flow will go through each pipe. And what we know is where the water is going in and coming out of the system. That's a given at the beginning of problems like this. And so here you can see that there's 20 units of flow coming out in one node, 50 units of flow coming out at a different junction. Here this junction has 30 units of flow coming out, and then the 100 units that's going out has to also be coming in. And so it's here at this junction where the flow is coming in. So what we want to do in the Hardy-Cross method is determine how much flow goes through each of the pipes in the network. And in that simpler example that we worked through on Friday, we developed this idea of R, where R is just a resistance factor. And you can calculate R based on the Darcy-Weisbach equation. In this example, they were just given directly because I was trying to show you more about the method and less about calculating the resistance. It was just the structure of the method. But what we have to do is iteratively go through a flow balancing process where kind of the thing that we know is that at a junction, the flow in and the flow out have to be equal. And so we're going to start with guessing what the flow rate might be through each of these junctions. And then we're going to check and see if we have a guess, then how does the energy equation match up? Essentially, you know, if you have a guess flow rate through each of these pipes, what you should be able to do is go to a location by different routes. For example, if I'm going from this lower junction up to the top one, I should have the same head loss if I go directly through this pipe or if I go indirectly. And if I have a different amount of head loss, then that tells me that the flow rates aren't quite right. And so this procedure that we're going through, the corrections that it makes are based on getting the same amount of head loss from one point to another, regardless of which route you take to get there. So that's the fundamentals of this process. In the second example, we're going to start off by you taking a moment to identify the initial flow direction and write the guess flow rates on the paper. What I had sent you before the class on Friday was, let me just pull it up real quick, the handout. All right, so here's the handout. It's coming up just now. Today we're going to be working on this example. So if you have this printed out, that's great. If not, draw this on a scratch piece of paper. The first step that we're going to follow here is you're given that the flow in at junction A is 1 cubic meter per second, and there is 1.2 cubic meters per second going through junction D, and there's 0.6 cubic meters per second coming out at junction B, and then there's also an outflow at junction E. But what we don't know is how much flow goes through each pipe. So for example, there's 1 coming in at A. What happens then? So the first thing you have to do is come up with a guess. You have to draw like a little arrow on the paper to indicate the flow direction, and then you have to guess the amount as well. So for example, what you could do is you could draw an arrow. Let me see if I can get my drawing tools here. All right, so you could say the flow goes that way, and then there's also some flow going this way, and then guess the amounts. So if it's 1 coming into A, then you could say 0.1 is going down here, and that would mean 0.9 goes this way. And it doesn't matter how bad your guess is, really. If you have kind of a really unlikely guess, eventually the solution is still going to converge as long as it all adds up at each junction. So you couldn't say, if 1 comes in, you couldn't say that you have 20 cubic meters per second going down and 50 cubic meters per second going this way. Your solution is never going to converge if you violate the continuity principle at each junction. But if you said like 0.1 and 0.9, since it all adds up to in equals out at the junction, then you're going to eventually get an answer. You could do, instead of 0.1 and 0.9, you could do 0.5 and 0.5. And it's still all going to work out. But then what you also need to do is consider these other locations. So for instance, here, if I said, let me do some more sketch tools here. Okay. So let's say that I want this one to be 0.3 cubic meters per second, and then I'm going to let this one be 0.7. All right. So now look at junction B. If I have 0.7 going into junction B, and this 0.6 is being taken out of junction B, then what does that say about the leftover 0.1 cubic meters per second? Where does it need to go? Well, I think what that means is that the only option is that the flow is going to be going down here. Then the flow that's left is 0.1. 0.1. Okay. So now flow balances at junction B because I've got the 0.7 in and 0.7 out. Some of it through pipe BC, some of it is drawing out externally. All right. So the next thing I got to do is look at junction D. So you've got a certain amount of flow coming in, 1.2. You need to split it. Okay, now I'm going to stop and ask that you come up with your own flow rates and directions for every pipe in the network. So I'm going to give you 3 or 4 minutes to think through this, and then what we'll do is we'll start putting this all into the spreadsheet template that I also emailed out last Friday. Okay, so I'm going to pause for a moment, and you either write this on the paper that you've printed out or recreate this on a scratch piece of paper so that you can start sketching the flow balance. All right, let me show you the flow balance that I settled on, and if you're stuck, maybe that will help move you a little bit down the field. So here's our system, and the flow balance that I settled on is here. So these are my initial guesses, and so there's no single right answer, by the way. If yours don't look like this, that doesn't necessarily mean that you're wrong. The only thing that would make it wrong is if at any of the junctions it doesn't add up to the in equals out. So let's see if I'm right. Okay, so at A, in is 1, out 0.5 this way, 0.5 that way. All right, fair enough. Now let's look at D. D, I've got 1.2, so I split it 0.6 and 0.6. All right, now that's not a good guess, by the way. Look at these pipes. I've got a 500 millimeter pipe versus an 850 millimeter pipe. So remember earlier in a previous lecture, it might have been Wednesday, when we were saying, you know, is more flow going to go through one pipe versus another one, you know, based on which was the longer pipe, which was the rougher pipe, which one had the larger diameter. Hopefully you remember that. We were talking about it in the context of the nodal method. But the same principle applies here, where in reality, if you have 1.2 coming in, there's less resistance between pipe CD than there is through pipe DF. And so maybe a better guess would have been like 0.8 going up, and then that would make it 0.4 going to the left. And you know, the solution may converge faster with fewer iterations if you make good guesses, but I'm making simple guesses. I'm splitting it half and half. Okay, so we've got both of our inflows split. And so now what does that mean here at pipe EF? So I already defined the 0.5 coming down towards F and the 0.6 coming from the side to F. So that means that if you've got 1.1 coming into F, 1.1 has to go out. And so if you look at what's happening with E, there's the 1.1 coming in from F and 1.6 going out, which means I have to be feeding it with another 0.5 from CE. Okay, now if I have the 0.5 going from C towards E, then the 0.6, there's going to be a leftover 0.1, and so now it all matches up here at junction B because the 0.1 plus the 0.5 that I determined at junction A combined together means an inflow of 0.6 and the external outflow is 0.6. So here's my initial guesses. Yours can be different, and in fact, if you want to use your initial guess flow rates in the example that we're about to do with the spreadsheet, that's fine. I'm going to be using these guess flows as we start up Microsoft Excel. Before we do, are there any questions so far about this flow balancing part of it? All right. So then this is where the fun begins. Here's the template, and we've identified the loops. Okay, now hold on. Back to this process here. How many loops are there? Okay, there's 2 loops. So we need to label them loop 1 and loop 2. So I'm calling the upper loop loop 1, and the lower loop is loop 2. All right. Next step. What is N? N is determined by what friction loss method you're using, whether you're using the Darcy-Weisbach equation or if you're going to be using the Hayes and Williams equation. So here on the handout, I tell you that if you're using Darcy-Weisbach equation, n is 2. If it had been the Hayes and Williams equation, n would be 1.85. So we're using 2 for n. All right. Define the direction. What that means is that we're going to assume clockwise is the positive direction, and any flow that goes against clockwise is a negative direction. And so back to this example. Here you can see my initial guess flow rates. When I put in the flow rate for pipe AF, I'm going to call that minus 0.5 because it's anti-clockwise. Think about a clockwise direction. Can I draw that? Certainly not well. All right, let's try that. Okay, and I'll put an end on that. Oh, this is going to turn out great. Oh, is it a picture though? A line, solid line with an end. Oh, I suppose it's not worth it. I'm not able to put an arrow on the end of that. If I would, I'd put the arrow here at the end just to define our direction. Clockwise is positive. So if clockwise is positive, then that means this 0.5 meters per second from A to F is negative. But if clockwise is positive, then AB is a positive 0.5 cubic meters per second, because in the context of loop 1, this is the same direction as clockwise, but AF is anti-clockwise. Okay. Now assign the guess flow rates you've already seen. Assign R values for each pipe. All right, that's where we'll start getting into the spreadsheet here. All right, so in iteration 1, let's put this on here. So iteration 1. Okay, now I'm going to start typing in the data for loop 1, and I'm going to begin by defining what's going on with pipe A, B. A, B. Okay, now the K sub S of this pipe, let's see, was that defined in the example here? All pipes have a K sub S or an epsilon of 0.3 millimeters. All right. So we're going to use that to calculate the resistance. So 0.3 millimeters, so I'm going to do 0.3 divided by 1,000. Okay, and the diameter of pipe AB is 500 millimeters. So I'll just put 0.5 meters. Okay, the area, pi times d squared divided by 4. Now I've got the cross-sectional area for that pipe. The length of pipe AB is 220 meters. The F value, I'm going to start off by assuming fully turbulent flow. Okay, so remember, here's the full Jane equation. For the fully turbulent flow assumption, we don't yet know the velocity, so we'll just assume Reynolds number is really big, and the F value only depends on the left side of the denominator there. Okay, so I'll type that fully turbulent version of the Jane equation in, equals 1.325 divided by, parentheses, logarithm of K sub S, that's in meters, divided by 3.7 times D, close parentheses, and I need to square the denominator. Okay. So if it's fully turbulent flow, then the F value is going to be 0.0178. Is that right? Okay. Now R is defined. Here's our formula for R. It's the F value times the length of the pipe divided by 2GA squared times D. Okay. So it is F times L divided by 2 times G. Now we're in SI units, so G 9.81 times A squared. So here's A, we'll square it, and multiplied by D. Okay, so that's the R value for this pipe. Now N, we said since we're working in Darcy-Weisbach for our friction method, N is 2. The flow rate is the guess flow rate. Okay, so my guess flow rate that I'm starting with here is 0.5, and it's positive for pipe AB. Okay. Now, I'm going to wait to do the rest of these until I've filled out the other pipes in loop 1. So there's pipe AB, then there's also pipe BC. Okay, and that has the same, all the pipes have the same equivalent sand roughness. The diameter of pipe BC is 0.65. Okay. And so then that means I can drag down this formula for the cross-sectional area. The length of BC is 100 meters. And then the F value can be estimated in the same way. The R value and the N value. And then I need to type in the Q. So the Q here, it's anti-clockwise. So I'm going to have negative 0.1. Okay. Now we're looking at CE. Now we have to be careful about these pipes that are in both loops. And we're right now working in loop 1, and so pipe CE, when I indicate its direction, it's going to be positive because the flow is from C towards E. And so that's positive 0.5. But if I was looking at pipe CE from the perspective of loop 2, then that would be a negative value. So one of the common mistakes that students make is when we're switching between loops, they're forgetting to change the sign on pipes that are in common between both loops. So I'll show you what I mean about that and how to overcome the issue in just a moment. Okay, so let's put in pipe CE. Okay, so pipe CE has the same K sub S value as the others. The diameter of that pipe is 0.6. Now the cross-sectional area can be calculated automatically. The length of pipe CE is 150 according to the drawing. The F value can be calculated with this fully turbulent flow assumption. And the R value is derived from all the F value, the length, the area, diameter, and so on. N value is still 2. And then for the flow rate, since it's from the perspective of loop 1, it's clockwise direction, that's positive, so 0.5. All right, the other pipes that are still in loop 1 is pipe EF. All right, so pipe EF is the same diameter, the same equivalent sand roughness. The diameter, 0.7 meters diameter. The length is 80. And we want to carry through both the F value and the R value. I guess we can and also repeat the N. And then the flow rate we need to put in, it's minus 1.1 because from the perspective of loop 1, if positive is clockwise, this is anti, oh, the N changed. Thank you for noticing that. All right. And then last pipe in this loop is AF. Okay, so the K sub S, the diameter 0.4 meters. It automatically calculated. That's kind of nice. The length 180. Oh, and it got the R value. Excel is getting smarter. It's gone fully AI on us. 2. And then the Q value is negative 0.5, so minus 0.5 because it is against what would be considered clockwise in the perspective of loop 1. Okay, so now we've got all of that data. Any questions so far before we move further? Before we go any further, all right. R times Q times absolute value of Q. So R times Q times ABS for absolute value of Q. Okay. I'll drag that down through all of them. Now R times N times R times absolute value of Q. So N times R times absolute value of Q. Okay. And now the delta Q. Let's see, where do we have the formula for delta Q? Here it is. Let me paste it in. Oh, I'm surprised it's not already in that template file. What was I thinking? There it is. Let me put it down here so we can see it good. All right. So the delta Q is going to be, we're going to rely on the sum of this and the sum of that. So let me get a summation below there. So the sum of these things for one of the loops and the sum for the other. And then just to kind of break it up visually, what I'm going to do is I'm going to make this italics. And hopefully it being in italics there will help remind me that this isn't for an individual pipe, but it's the total for all of the things that are above it. And so then the delta Q is equals negative the sum of the R times Q times absolute value of Q divided by the sum of N times R times absolute value of Q. Okay, so this is a correction factor that we're going to apply to every pipe in the network. And the next thing I'm going to do is type that formula in again. I'm not going to drag it down. I'm not going to anchor it. I'm going to type it in as many times as it needs to, because in the long run, as you'll see, it's less time to do that. So equals minus this divided by that. Because when we drag this down and repeat it in subsequent iterations, we don't always want it looking up in the same spot up here. We want it to look in the new loops. So we have to type in that correction factor formula for each row. Okay, so now this was the original guess flow rate, and this is a correction factor that's being applied. So the corrected Q is going to be our original guess of the flow rate plus the change. Okay. Now that I can drag down through all of them. So I now have an updated flow rate. And let's calculate the absolute velocity. So that would be ABS for absolute value. And then V is Q divided by area. So Q divided by area. So now this tells me the speed of the flow through the pipe, which I can use to calculate the Reynolds number. This water, I think, is just ordinary water at an ordinary temperature. So I'm going to use the typical kinematic viscosity of 1 times 10 to the minus 6th meters squared per second. So calculate the Reynolds number here equals velocity times diameter times the, divided by the kinematic viscosity of water. So 1e minus 6. So now I've got the Reynolds number for each pipe. And then this percent change is an indicator of how much the flow rate changed during this iteration. And I'm going to use this to know like whether my solution has converged. So how much has the flow rate changed? It's going to be the new flow rate minus the old flow rate divided by the new flow rate times 100. Okay, so 17% change. Some of these pipes are going to change quite a lot. BC, chief among them. All right, so now we are going to look at loop 2. That was the lower loop. So we'll put in all the data for loop 2. By the way, don't worry. A lot of the data entry that we've done is going to become automated in subsequent iterations. So we'll just be able to copy and paste, and then Excel will continue the calculations and converge until we know the flow rates. All right, so here in iteration 1, loop 2, we have pipe CD. So CD, now all these pipes have the same K sub S value, so that was, just to remind you, 0.3 divided by 1,000. Okay, pipe CD has a diameter of 0.85, and then the area we can calculate, I just pasted the formula for the area and it looked at the diameter. The length is 80 meters for pipe CD. Let me just put in all the physical constants, all the pipes here. So there is DF, EF, and CE. Okay, they all have the same K sub S. The diameter of DF is 0.5. The diameter of EF, 0.7. Diameter of CE, 0.6. Okay, now their lengths: DF, 200, EF, 80, CE, 150. Okay, now the F values I'll calculate the same way I did before with the fully turbulent flow of the Darcy-Weisbach equation. So we're neglecting any estimate of the Reynolds number in this first iteration. Okay, we calculate our F values, and then we can get the R values. I think I can just copy this and paste it and drag it down, and it'll determine the R values based on what's to the left. N is just going to be 2 for all of these. Now the flow rates I have to put in. Okay, CD, what was my guess for CD? Let me zoom out a bit so that that's visible. CD is minus 0.6. And there's just so many ways you can screw up these calculations. If I put 0.6 instead of minus 0.6, then the solution is never going to converge. So literally all it takes is a single minus sign in the wrong place, and this method isn't going to work. So attention to detail is paramount. So minus 0.6 for DF is positive 0.6. Oh, hold on a minute. Yeah, DF. Yeah. Okay, positive 0.6. EF. Now, EF, I would have said 1.1 because that was my initial guess, but I have a better guess for that because look, EF is here in this loop, and it's also in this loop. And the same thing is true for CE. CE is a common pipe in both loops. So I'm bolding it just as a reminder. All right, so now what I do for EF is I don't just use my initial guess of 1.1 because I can do better than that. I have an updated guess. And so I'm going to say it's based on this corrected Q from the other loop. So equals minus of that. And minus because I know it's going to be positive from the perspective of direction in loop 2. In other words, from F towards E is a positive value. In loop 1 we called that negative because the flow is going from F towards E is anti-clockwise. But when I'm in loop 2, from F towards E is clockwise. Okay, so that is why I put the minus sign in referring to that other one. And so then I take the same approach here. Equals minus, and I'm going to use the updated value for the corrected flow rate CE. All right. Now I need to do both of these calculations. I'll just paste that, and it applies the R times Q, absolute value of Q, N times R times absolute value of Q, and then I can drag it down through both of them. And then I want a total, so sum. And I want the sum of, let me italicize that, just as a visual indicator that that's not just an ordinary pipe-based calculation, but it's a total for that loop. Okay, then this formula again. Okay, so equals minus this divided by that. Equals minus that divided by that. If there was a good way to automate that and not type it in again, I'd take it. There's not. So we're better off just typing it. All right, so then our corrected flow rate will be our original guess plus the adjustment factor. Now we have an updated value for the flow rate for each of the pipes. And we can likewise calculate a absolute value of the velocity, a Reynolds number, and the percent flow rate change for each of them. Okay. We're almost through this. It may not seem like it, but we are going to finish this before class. Before class ends. We're now in iteration 2. Now what I can do is I can copy and paste all of this. That's the same from iteration to iteration. So Control C, Control V to paste. So the physical contents of the pipe name, the roughness, the diameter, the area, the length, that's all the same. I don't want to use the fully turbulent flow assumption again, though. This time I'm going to use the full Jane equation because I now know Reynolds numbers. Okay, so let's use the full version of the Jane equation. So now our F value is going to be equals 1.325 divided by the logarithm of K sub S, here it is, divided by 3.7 times D. All right, so far so good. Plus, now we're doing the right side of the denominator, 5.74 divided by the Reynolds number to the 0.9 power. So I'm just going to refer up here for the Reynolds number and take it to the power of 0.9. Okay, now I close out that, and I got to give it a squared term. It should be relatively close to the other one. I mean, it's going to change a little, but if it changes dramatically, we've typed the equation wrong. And it hasn't changed dramatically, and we haven't typed the equation wrong. Although it looks like the font is different. That's strange. It looks smaller, doesn't it? Oh, yeah, 9. I don't want it 9, I want 11. All right, so I can drag that down for all of the pipes. We have updated F values that are in kind of the range we're expecting them. BC is a little bit strange, though, because there's so little flow going through pipe BC. That's why we've got this kind of, for now, ridiculous F value. Hopefully, it'll get a little bit less crazy towards the end. All right, so what about R and N values? Well, we can just copy all of this, Control C, and paste it, Control V. So it automatically updates. Now for the flow rates, we're not going to key those in manually. We're just going to refer to the previous flow rates. And so where's the best guess for AB? Well, AB is not one of those common pipes. It's only in loop 1. So I'm going to say equals, here's my guess for AB right there. BC, here's my best guess for BC. Best guess for CE, it is down here. So I'm going to say equals minus this one. Okay, and where's my best guess for EF? The latest and greatest is equals minus, here it is. And then AF is only in a single loop. So AF, my best value for guess of flow rate is that one. Okay, now all of this, in fact, all of these, we can go this far. I think we can go this far, that far, that far. So we can do all of this in a single paste. So Control C and Control V. Okay, so what it's done is it's calculated our correction factor. It's pretty small. It's getting smaller, which means we're getting close to convergence. This first time we changed the flow rate by 0.1. This time we changed the flow rate by 0.01. So the percent value changes are getting smaller. That's a good sign. Okay. Now let's take a look at the flow rates here. So CD, my best and latest greatest flow rate of CD is this corrected flow rate. DF is here. But now EF, the most recent calculation and update for EF is right here. And I put the minus sign because I'm getting the flow rate from a different loop. And the same thing here, equals minus and the CE. Okay. Now I can copy all of that. Control C, Control V to paste. Well, there's an issue. Yeah, I pasted the wrong thing. I should have copied, oops. I should have copied this one. Here we go. Because there's more pipes in loop 1. So it's just simply, it was including an extra row. Okay, so Control C and Control V. That's more like it. Yeah, now we don't have odd values. So the flow rates are changing, with the exception of this one pipe BC that has just very little flow through it. We're already getting pretty close to convergence, just in the second iteration. The third iteration is where things really shine, because what we can do is we can copy everything, the whole thing, Control C, Control V, and the only thing I have to do is just change that from iteration 2, and I'm calling it iteration 3. But everything else is updated. Now you look, the flow rates, with the exception of this one pipe where there's hardly anything going through it, and so on a percentage basis, any correction is going to be relatively large. All the rest of them are less than 1% different. And you'll notice, take a look at the F values. From iteration to iteration, the F values have stabilized as well. 178, 178. BC is the exception because there's not much flow going through there, but it'll settle down eventually. CE, 0.172, CE, 0.171. So pipe C is stabilized. Let's do a fourth iteration just because it's easy. All we have to do is change one thing. Control C, Control V. And now change that so that it has the label iteration 4. And now even pipe BC finally is starting to converge, where our percent change in flow rate is just 1.2%. So if we're really nuts about it, we could go to a fifth iteration and see if we can get it under 1%, because that's kind of the standard. You know, if you can get every pipe to be less than 1%, and there it is converged to within 1% of the original value. So here you can get the flow rate for each one. It looks like if I do that fifth iteration, it's going to go on top of the rest of my template file. But you can see here's Our final flow rate for AB is 0.581. This is the answer from a previous semester when I was using this template. So what we're going to do when we get together in class on Wednesday is we're going to calculate the pressure at each junction. So we've determined what the flow rates are, and on Wednesday we'll use the flow rates to find out if we know the pressure at A is 600 kilopascals, then what is the pressure at every other junction inside of this network. All right, you really drank from the fire hose today. If you made it through that whole example and you actually got the same values as me, that is really a beautiful thing. And if you didn't, that's totally to be expected. Normally in an ordinary semester, I'd be circulating around the classroom, debugging spreadsheets, looking for mistakes in what you've done, and we'd go through it and figure it out eventually, but it's just so hard for us to collaborate in that same way in a virtual environment. So I'm really sorry that we're not together today, because this example in particular goes a lot easier if we are. Just to touch on these announcements one last time before we go our separate ways, remember homework 4 is due on Wednesday, but if you can't do that, let me know and we'll work something out. All right, that's it for today. Thanks everybody. Appreciate you being here. Hope you stay safe and stay warm and don't have to walk down the driveway in your socks anymore. Bye-bye.